going to talk about how to extend the Perl language, Perl 5 that is, by inventing new bits of syntax. Now, here's some syntax extensions that we've had for a while. We've had the facility to do this sort of thing for a few years. These are real examples. The top one is from the try-catch module by Ash Berlin. That's giving you a Java-style try-catch operator. And then the one at the bottom is taken from my employer's code base. This is declaring a method that's going to be visible to remote callers through the API. And the declaration syntax makes use of our internal type system. Those were both implemented using Devel declare, a module that's been around for a while. Very nasty hack, it lets you lie to the compiler in interesting ways. But in recent years, we have some new developments whereby you don't have to lie in order to do this. So I did a talk last year on this subject, talking about the new facilities in Perl 5.12. And they look a bit like this. Once you get into your custom parser code, I'll talk a bit later about how to get into the custom parser. Once you're in the custom parser, you get to look at what's in the parser buffer. You get to read character by character. You can parse your own syntax as long as you're prepared to do it character by character. The only real help you get with syntax is this function to parse white space for you. And once you parse wherever you want, you get to return an octree representing whatever expression you've parsed. Of course, you've got to build the whole octree yourself. You don't get much help with that, and often that's not enough power. So there's this escape hatch, these stuff functions, that if you can't parse everything you wanted yourself, then you get to fool the compiler a bit by injecting new source and pretending that was in the program originally. That's the kind of stuff that you did with Devel declare. That was the only way you could do it with Devel declare. But now you have the advantage that once the parser has invoked a custom parsing code, it's expecting the buffer to change. So you're not lying into it so much. So I talked about that last year, and I said that next year it'll all change. Well, now it's next year, and it's all changed. Now you've still got those facilities, of course, but what was really lacking was a way to embed bits of standard Perl syntax in your custom syntax. And that's what's new. Here, these are the new APIs in 5.14. You can call back to the main Perl parser and say, I want an expression. And in a totally recursive descent style, it'll parse whatever expression is coming up next and then return control to you. You can ask for expressions at various levels of precedence there. You can also ask for a code block, which is another thing you're very likely to want to do. And if you really want to mess about with the statement syntax, there are various parts of it down here. So here's what these bits you can parse actually look like. These are expressions at various levels of precedence. I've got a single expression statement, which is just an expression followed by a semicolon. Now, if you ask for an arithmetic expression, that can include the arithmetic operators, multiplication and addition, but it can't include the comparison operators or anything looser binding than that. The reason why this is picked out and named is that this is the precedence of the argument of a unary function if the argument is not parenthesized. Then we've got term expression, that's a term of a list, so it can contain operators up to a comma, it ends with a comma. A list expression, as the name suggests, is a list of terms. That can contain comma operators, and of course this is the precedence of the arguments of a list function if it's unparenthesized. The list expression does end at these special low precedence logical operators, and then we've got a full expression which can contain any of the infix operators. There is one very important type of expression, one level of precedence that I forgot to name and you don't get help with, and it's this one. If you need to parse an atomic expression at the moment, you have to make things up, do the old-fashioned way. I've already run into the need for that. Now, just a reminder, if you've got a bracketing construct, then your expression has to end at the same level of nesting that it started. So for those expressions here that start inside the parentheses, they have to end inside the parentheses, even if they could take the next operator that's outside the parentheses. Every expression is ended by a close paren. But conversely, if you started outside the parentheses, then no matter how tight a binding you are asked for, you can accept arbitrarily low precedence operators if they're inside a bracketing construct. You always take the full bracketed expression. And then here's the statement syntax, which is a little more complicated. Working from the outside in, we've got a code block which consists of a pair of braces. Inside the braces is a statement sequence, which, as the name suggests, is a sequence of 0 or more statements. Each complete statement, which we're here calling a full statement, consists primarily of the main thing you call a statement, which here is a bare statement, and then an optional label on the front. Now, there used to be an irregularity in the grammar here. Certain types of statements, such as package declarations and use directives, couldn't take a label, and that would have made the statement grammar more conceptually complex, unnecessarily so. So for 514, that's been simplified. You can now put a label in front of any statement type. And another loosening is you can have multiple labels in front of a single statement. And of course, statements nest as well. You can see with this while statement, the best part of the while syntax is a nested code block, and within that code block, of course, we have a statement sequence, which here consists of a single statement. By using these new functions, you can invent arbitrarily complex grammars and implement them in a recursive descent style. You can nest standard Perl syntax within your custom syntax, and then, of course, the standard sub-expressions can contain custom syntax themselves. So, I'll now talk about how you get your custom parser invoked. This is what I showed you last year. What you have to do here is you have to hook this plugin chain, and then once you get invoked, you have to recognize your magic keyword yourself, and you have to decide for yourself whether your keyword is active, and then you get to invoke your real custom parser. And this is awkward. The keywords don't obey any namespacing rules, so you can get clashes between different plugins. And of course, it's a lot of verbiage. And in 514, the core still only offers that, but I don't recommend that you use it, because we now have a prototype of an API that I want to get into 516, which is going to be a lot easier to deal with. And it looks something like this. At the moment, it's provided by this module. You have to include this extra header at compile time, and you have to load this module at runtime. But once you've got that, you then have this fairly simple function, cdset CallParser, which attaches magic to a subroutine. The magic you attach is the name of it's a C function that implements the custom parsing and an argument for the custom parser. And the subroutine that you attach it to fulfills two roles here. First of all, it manages namespacing. The custom parser is invoked when the name of the subroutine is seen, and whether a word is the name of the subroutine depends on the context. You can export the subroutine in perfectly normal ways, import it. You can import it under a different name. You can play all of these games. Import it lexically if you want with those modules. So the namespacing is now all sorted out. And the second job it performs is it provides a structure for the op tree that will get built in the end. Your custom parser doesn't now generate the entire meaning of the expression, including this keyword. Instead, it's just nominally parsing the arguments for the subroutine. It returns op tree representing the arguments, and then you get out of it a subroutine call op tree with those arguments, calling that subroutine. Now, sometimes what you want your custom syntax to do isn't a subroutine call, but don't worry about that. I've got a talk tomorrow, which you should all go to, about bending semantics, which will explain why that's not a problem. You can turn a subroutine call into anything you want. For now, if you're inventing new syntax, it suffices for it to be the syntax for a subroutine call. So here's an example that I used last year. I didn't use this in my Yapsy talk, but I used it in an earlier talk where I was talking about what you could potentially do with the 512 features. Here I've got a conditional construct which uses a slightly different syntax from Perl's standard if. It's using code blocks for the conditional expression of what to do if true and what to do if false. And it comes in two forms. At the top we've got a statement form, and you see it doesn't need a semicolon on the end. But the one down at the bottom, it's embedded in an expression. It's decided that it is an expression rather than a statement. And which one whether it is a statement or expression depends on whether it's got this parenthesis immediately after the keyword, which is having both expressions and statements in the language. It's kind of convenient to be able to use and operate both ways. Now, I never actually implemented this because it's rather awkward with 512. If this was what you could potentially really push the boat out, might manage. And the difficult part, of course, is that it needs code blocks. Parsing them, it's just impossible with 512. You can't do it properly. The only way you could potentially implement it would be to inject code to fool the standard parser into handling the block next. You get to play games with B-hooks, end of scope, that's useful. But now with 514, it's easy. Here's my custom parser for the myif subroutine. We don't actually want a subroutine call, of course, but we have a nominal subroutine. So we start out by going character by character, skip space, check the paren character by character, and then we just go parse block, parse block, parse block. And that's the difficult bit done. And then down at the bottom, we handle the close paren, that's character by character, very simple. And then we set a flag to say whether we're being a statement or expression. And then we just build up a list of the op trees we've got for these blocks. That's it. And the op tree that results from this will, of course, call the myif subroutine with the result of evaluating all three blocks, which is very much not what we want. So I'll give you a quick preview of the kind of thing I'm going to be doing tomorrow. It involves writing another subroutine that gets attached to the myif subroutine, and this operates on the enter sub op tree which represents the subroutine call, and it basically pulls the arguments apart and pulls the arguments apart and pulls the arguments apart, and down at the bottom finally gets to build an op, and it just builds the conditional op that function is provided by the call. So that does what you want. And the Devel CallParser module also gives you some bonus recursive percent parsing functions. These are the standard argument parsers. This is the default behavior for parsing the arguments of subroutines. There are four different syntaxes. There's nullary syntax that won't accept any arguments but will accept empty parens. There's unary, talked about. There's list expression is the default, and then there's block list. That's a list with an optional code block on the front. That's it if you're trying to imitate map and you use the ampersand prototype. And then down here, this is actually the ultimate default that you get you get it parsed according to whatever prototype the subroutine has, or in list form if it doesn't have a prototype. These are useful. Partly they're conceptually completing the system, but they have a practical use if you want to wrap them in order to modify their behavior. So here's the last trick I'm going to show you, which you can do with the new system. In this case, I've got a subroutine. I actually want to call the subroutine, not worrying about the semantics, but I don't want the argument to be evaluated up front. Instead, I want to wrap up the arguments in a closure, which in this context is called a thunk, and I want to pass the closure to the subroutine. So the subroutine gets to decide when and if the arguments will be evaluated. So, having intercepted parsing, I need to set up this environment for parsing a closure. It is an inconvenience of the Perl parser that every expression at the time of parsing has to know which subroutine it's going to be in. So having done that, I then hand off to this standard parser, which is just parsing the arguments of a list subroutine. I don't have to get my hands dirty at all. I haven't looked at characters at all. And having done that, I then finish off the closure and generate the closure expression, and that's it. And that's amazingly useful. What I want is I want a lot of out-and-proud benders. I want people to play with this module, Devel CallParser. Look at that module and look at this part of the API, which provides you with the help with looking at characters. And then these two modules are modules I've written that use Devel CallParser. You can use them as examples of how to do things. So thank you all for listening. I'll take questions now. Jesse?
Have you considered a pure Perl API?
Certainly have considered a pure Perl API. It's more work than you might expect. It's not just a matter of hooking pure Perl code into the parser. That bit's relatively easy. That would be that module would naturally be called CallParser. The really difficult bit is the amount of support you need in order to do anything useful once you've got there. We need pure Perl bindings for all of that Lexa API and all the parser functions, and quite a lot of ob building stuff. And most of that is missing at the moment. So it's on the cards, but it's not my priority. Next. Anyone? Hey, yes?
No. If this is 1.5.16, 1.5.5.18.
What do I want for 5.18? Well, I'd rather like to turn a lot more of the Perl standard grammar into this format. I'd like to go much more recursive descent. I'm a little worried about the potential for blowing the C stack. We might have to look at options for fiddling with that. Basically, I'd like to pull the grammar part and put it all into recursive descent styles so that you can call into any part of it, not just these few important parts. I'm also looking at the potential for plugging in custom infix operators. There are two aspects of it. Partly it's having them in an infix location, and partly we want to be able to spell operators using punctuation characters. We're going to need some kind of longest match thing. It'll be a new way of looking up names of what are otherwise subroutines. Okay, up there?
Yeah. Is a subset of this backportable to default pricing?
A little bit of it is. The Devel CallParser API works, the module partially works on 5.12 because it's layered over that old keyword plugin mechanism. So you get that side of it on 5.12, but not any earlier. Now, being able to call the standard argument parsers does require 5.14 because it's built on top of the calls expression parsing functions. So it got limited facilities. If you need to go earlier than 5.12, then you have to use Devel Declare, or actually Matt is trying to push his new invention, Devel Declare Evil, which has the advantage over Devel Declare that it doesn't require any excess that's not in the core distribution. It uses B. It uses some of the B modules to look at reference count to figure out whether a name that was in the source was referencing something of interest. So play with double declare and double declare evil if you need to go earlier. Okay. I believe it's now officially lunchtime. So thank you all for listening.